So today we are going to be moving into the lithosphere. And so the lithosphere is the rocky outer part of the Earth. I'm lithosphere. So far we have been focusing on geography in a more general sense, and so we're now starting to really get into the Earth systems, and the first one is the rock cycle, or um, generally like rocks, but the lithosphere is the actual sphere. And so we'll start kind of by the inside of the Earth and work our way out. So we're going to be talking about the interior of the Earth, what's under the ground, and yeah, the crust, all of that. You shall see soon. So here's two fun videos. Uh, to watch. I think they're both just kind of fun. The second one you should watch. Both of them you should look at. They're good. Last time, so in our last lecture, we talked about maps and map skills, projections going from a round Earth to flat maps, distortions, and GIS, GPS, topographic maps, and PLSS. So today, like I just said, we'll be talking about the lithosphere, and more specifically, we're going to talk about the Earth's plates. So the surface of the Earth is actually broken up into different plates. So we'll be talking about that, the interior of the Earth, and then how those plates move around using a theory called continental drift. So let's journey to the center of the Earth. There's books and movies that use this title, so I'm stealing it. Both of these links give more like a visual in depth to the interior of the earth and how the earth came, like the formation of the earth. So watch both of those. I'm not going to click them and play them in this video. Uh, but I'm going to assume that on your own you watch these. They're pretty short and they just give you a visual of the things that we're talking about. Oh, I keep okay. So, before we start talking about what's in the earth, let's talk about how we know what we're about to talk about, right? So like the source of our information. We understand the interior of our earth by looking at waves that happen from earthquakes, and those waves are referred to as seismic waves. And so when an earthquake happens, there's energy that travels through the earth in the form of waves. And when we measure those waves or look at those waves, we can see what they've interacted with in their journey. So there's two different kinds of waves, P waves and S waves. So P waves we refer to as compressional waves, and S waves we refer to as shear waves. So the two images are showing you in this first one, you should still be able to see my mouse. If there was an earthquake that happened at this point, energy from that earthquake would radiate out in all directions, across the top, in all directions, right? Those waves, there's both kind, P and S waves happen during that. And so those waves either act like compressional waves. So this first column is P waves, compressional waves, and that is almost like an accordion, right? So the ground doesn't wave up and down like you think of a water wave. Instead, it like an accordion goes in and out, right? So these darker lines are showing where the ground is like squished together and it's stretched out in between, and that scrunched up and stretched out pattern travels throughout the ground, right? If these blocks are representing the ground. And then the S waves do act like what you think of when you think of a water wave. So it's not squishing or anything, but it's more traveling up and down. I like to think of it as like in the gym, you know, those big ropes that you like wave up and down. It's kind of like that. So understanding that there's these two waves that are both released during earthquakes, and sometimes we'll like set off bombs and stuff, not bombs, but like, you know, dynamite and stuff in the earth to create these waves as well. But we know that P waves can go through both liquids and solids. So when P waves are traveling, if it encounters either a liquid or a solid earth, the P wave will continue moving. And we also know that P waves can go faster through material than S waves do. So if P and S waves are racing, P waves will win. S waves, on the other hand, are slower and they cannot go through liquids. So if there's an earthquake, and, well, okay, so here, let me show you. Pretending this is the surface of the earth. If this is where the earthquake was, and the waves traveled, and the entire inside of the earth was the same, like there was no differences throughout the inside of the earth, the waves would just travel straight through, and you could measure if there was a person standing here with a seismograph reading the seismic waves, here, here, there would just be a straight line. However, when there's a change in the material, so what we haven't talked about it yet, but like in density and also if it gets more or less like fluid, then the waves refract, right? So the lighter in the middle of the earth is showing a gradient change of material. And if the waves happened here, they would bend before hitting this point, hit this point, this point, this point, so on. And we could measure that a couple of different ways: speed, timing, things like that. And then finally, if we're looking down here, these rings represent like an abrupt change in material. So let's look at this little bent wave here. This would be, we can assume, an S wave, and that this is a liquid ring, right, or liquid material. Because if an S wave came from an earthquake here, it would hit this liquid and it can't travel through, and so it would bounce off and come back. It could also do that. So it's just, I'm spending probably more time on this than I should because we don't have all of our information, but it's just showing that using the different characteristics of the S and P waves and looking at how it's traveling through the earth and where we're measuring the waves and at what time we're measuring the waves, we can understand what's going on under the earth. Because seismic waves will change their velocity, which is made up of both speed and direction, based on the density of a material and the elasticity of a material. So elasticity is referring to the ability of an object to retain its shape. So if something can't retain its shape, you might call it like rigid. Like a stick usually isn't very elastic, but a rubber band is, right? So a rubber band, you could scrunch it up. When you let it go, it goes back to being a rubber band. But if you were to scrunch up a stick, it would break, right? Density is, for our purposes here, just how thick something is. So something like a sponge is not very dense, but a rock is dense. And then speed in general of the waves increases with depth, and the increase with depth has to do with a couple of things. Pressure is one of them, and because of the pressure, the Earth's material is becoming more compact, and so the waves can travel faster through it. So by studying these different properties and how the waves are traveling through the Earth, we can see that there are changes in the physical properties in the interior of the Earth, and we divide up the interior by those physical properties. So, depending on the depth of the Earth, you get more pressure as you go towards the center, and you get hotter temperatures. And so the Earth can behave like a couple of different ways. One, a brittle solid, so something that shatters or breaks very easy. something that can deform in a plastic-like matter, so it might like it might you might squish it and it won't retain its shape, but it'll like squish instead of breaking, or things can melt and become liquid. And so using those physical properties and the mechanical strength, we can create identifications and classifications for the interior of the Earth. Oh, my keyboard is not working either. Okay, so Earth structures, there's 3 main layers, and then each of these layers are broken up into more defined sections. So the 3 main layers on the interior of the Earth, well, you have the crust, which is not the interior. It's the outer shell. So you don't have to memorize these thicknesses. I mention them so that you can get an idea of the relative size of each of these layers. So like the crust, it says it's the thin outer skin that ranges from 2 miles at oceanic ridges to 40 miles in some mountain belts. You don't have to memorize that. Just know that it's really, really thin compared to everything else, and it changes between 2 and 40 miles, so relative, so you know that it gets thinner in some places and thicker in others. Then you have the mantle. And the mantle is, we consider mostly solid rock. And it goes about 1,800 miles. So if the thickest part of the crust is 40 miles, then that should give you a relative idea of how thick the mantle is, really, really thick, if it's 1,800 miles. You also don't really need to memorize the makeup, like the silica rich. It's just giving you an idea of the differences. But in our class, we just need to know uh, the different sections and how they behave, not what they're made up of or their exact thickness. And then finally you have the core. The core is really iron rich, and its radius is 2,161 miles. So here is a pie slice of the Earth. So this is the Earth. We're looking at this section here. Your crust is the very top. Your mantle, is that showing? Yeah, okay, so here's the whole mantle. And then you have your core. And so each of those are broken up. The crust is broken up farther as well. But, well, I guess you can kind of see it here. We'll talk about it. But the mantle has the upper mantle and the lower mantle. And then you have the outer core and the inner core. So it's also worth mentioning that the crust can technically be lumped into the upper mantle. But for our purposes, we're going to talk about it in its own right. So this is the thinnest part of the Earth. It does vary in thickness, but even the thickest part is very, very thin compared to the rest of the sections. And you have continental crust and oceanic crust. So continental crust, for the most part, is land, like dry land. And oceanic crust, for the most part, is under the ocean. So again, these numbers are relative. The continental crust is less dense than the oceanic crust. The continental crust is thicker than the oceanic crust. And the makeup of each of the crust types are different as well. So the thickness or the density, let me start over, those are different things. The density of the oceanic crust is higher than the continental crust, and it's also thinner. So the oceanic crust doesn't actually sink, but I kind of remember that it's denser than the continental crust because I think that it's under the ocean, so it sank because it was too thick and heavy to float like the land does, like the dry land does, which is not at all how it actually works, but that's just a memory trick for myself. All right, so the mantle, this is what most of the Earth is made of. About 82% of Earth's volume is thought to be mantle. It's solid, rocky layer. And there's two main parts, the upper mantle and the lower mantle. The upper mantle is then further broken into the lithosphere, the asthenosphere, and a transition zone. So the lithosphere is rigid, and the asthenosphere is, it's not considered a liquid, but it flows. So maybe think of it like a lava light, right? Like if you can think of a lava lamp, hopefully you know what I'm talking about, and it has that material in there that goes up and down and it kind of bubbles and it's not really a liquid, but it's definitely not solid. You can think of it like that. And then the transition zone, so obviously, well, maybe it's not obvious. We cannot get down far into the earth. It's too hot. We don't have the ability to drill really far down. So we haven't seen these materials for ourselves. It's all off of different types of measuring seismic waves and whatnot. So we see this transition zone, we don't really understand it. There's an increase in density and it tends to hold more water, but we don't have more detail than that. And then underneath the transition zone, we have the lower mantle. And so its properties change a little bit, but again, it's too far down to really understand the details of it. And so the lithosphere is Earth's outermost sphere, and this is where the crust is contained. So as I mentioned, the crust is part of the uppermost mantle, and yeah, it's in the lithosphere. So it's relatively cool compared to the rest of the Earth. It's very rigid. Oh my goodness, I keep trying to, again, you can't see me, so this is weird. I keep trying to forward the slides using my keyboard. But in trying to fix my webcam, I messed up my keyboard, so I have to use my mouse. Anyways, so that's what those long pauses are. I'm like, why isn't it changing? Okay, the asthenosphere is beneath the um like the lithosphere, right? Obviously, we're going down. And so when we're talking about in a little bit continental drift and plate tectonics, the lithosphere is sliding around on the asthenosphere. So they act independently of one another. So the lithosphere on top is very rigid. What can we like? Oh, it's kind of like ice. And if like ice, in the springtime it breaks up and it moves down rivers, so the water of the river would be more like the asthenosphere, and the ice on top would be like the lithosphere. And then we have our transition zone, which we don't have a lot of information about other than it tends to hold more water and gets more dense. And then underneath we have the lower mantle. So the correct term for this is the mesosphere. The the mesosphere is thought to be of more rigid than the asthenosphere, but there's still very, very slow plastic flow. So it's not like a lava light. It's even slower than that, but the rocks can get really, really, really hot. And so maybe think of it like iron, right? Like um, what are those people called in the medieval times that would like bang on swords with their metal? Why can't I think of this term? But anyways, you know how like in movies they show you heating up iron really really hot and then they hit it with a hammer to kind of bend it. Think of it like that. So it can get hot and it can change shape, but it's not really flowing in any real way. And then finally you have the core. The core is pretty big. Um, It's smaller compared to, well, no, it's big. It's like the size of Mars. I'm trying to see what this is showing you. This picture, I feel like, is not good to scale. But there's two parts of the core, the inner core and the outer core. The outer core is a more liquid core, and the inner core is solid. The outer core is dense, and the inner core is growing, and it's growing because the uh, materials on the inside are still crystallizing, and so it's getting bigger. If you watch the video at the beginning, and it showed you how the Earth kind of started to solidify, that is still happening on the interior of the Earth. And so as it's solidifying and crystallizing and getting a structure, it's getting bigger. And then the core rotates independently from the mantle, and it rotates faster. So the outer core, see, it's the liquid core. Oh, there's convective flow within. So within the outer core, it has convective cycles. So big cycles where there's heat, like the material is heating and cooling, and that heating and cooling causes it to go in cycles. And it helps and contributes to the magnetic field around the Earth. And then the inner core, it behaves like a solid. It's stronger than the outer core, and it's growing. So here's kind of it broken down for you all in one. So you have like the overall bigger picture. You have a slice of the upper mantle. Well, actually, the mesosphere is there too. So this is the upper mantle from the 660 up. And then here is just the upper mantle. You have your asthenosphere, which is that kind of flowy sort of layer, and your lithosphere, which is really rigid. Technically, the continental crust is part, or not just the continental, the crust is part of the lithosphere, but we think of it as its own. You have your thin, dense oceanic crust, and your thicker, less dense continental crust. The boundaries. So when we're looking at those different sections, we understood where these sections were, not so much by the middle part, but where the boundaries are. So we saw that there was a difference in the behavior of the waves, and so we said, okay, well, something is happening here that makes between here different, right? Like we saw a difference in the waves behaviors here and about here, and we said, okay, well, in between there's differences. So what is going on in between there? And one of them, one of those boundaries is the MOHO. MOHO is usually always on the test. And you don't have to know when or who it was by, but we should give people credit because that's a pretty big discovery. And the MOHO separates the crust from the mantle. So again, the crust is technically part of the lithosphere, but for our purposes, it's the crust and then the mantle. And let's see what else. Oh, so there was a difference in the velocity of the P waves. And the depth of the MOHO changes across the surface of the Earth. So if you're looking at this image here, this line that separates this like dark gray from the dark brown, that's what it looks like on my computer at least, is the MOHO. It gets thicker under thicker continental crust, and it gets thinner under thinner continental crust. So if this is the crust, this top brown part, you can see that here's like the plains. Maybe this is where we are. There's a little bit of a dip. And then maybe this is like Colorado. There's mountains, and it goes down to the ocean, right? The MOHO, that boundary, separates where the crust and the mantle material is, but it gets deeper. I think I was using thicker and thinner before, but I should be using shallower and deeper. Is like the inverse of the surface of the earth. So you can see that here, like where there's a mountain peak, the moho is deepest. And then it goes back up. So where the continental crust, where the crust is thinner, it's shallow. Like it's towards the surface of the earth. So what this is showing you here is the crustal thickness. So red is like thicker, and then this like yellow color is the thinnest, and it's a gradient down. And so it's also showing you depth or shallowness of the moho, right? So here, where the crust is really thick, the moho is really, really deep down. And here, where the crust is thin, the moho is close to the surface. So it's the inverse of the thickness of the crust. That is usually a test question. And then you have the core mantle boundary. And so this was discovered using or discovering something called the P-wave shadow zone. So again, if we're talking about seismic waves happening from an earthquake, they have something called seismographs, and the seismographs are all over the earth. And so if there's an earthquake here, they will all, like, let's say each point of these arrows is a seismograph, they'll all eventually pick up those earthquake waves. And the timing and the strength indicate things about what those waves went through. And so there was this discovery that there was this P wave shadow zone, and it was because the behavior of the waves changed within the interior of the earth so that they bent and refracted, and none of them were coming through in this shadow zone because anything that hit them were bent. And so those mathematicians did their math stuff and they said, okay, well, if it's dying out from here to here, then the radius of whatever is bending it must be this big and it must be this material. And that's how they found it. Anything, I mean, we're still learning. It says this here is learning a lot about this layer. We're learning a lot about a lot of the layers. Um, but yeah, so that's kind of a given. And then we have an idea that the core changes. Like there's the outer core and an inner core. And this is because the P waves that were passing through the inner core showed an increased velocity. So it suggested that the inner core is solid because the waves moved through it faster than it did the liquid outer core. And so, as I've referred to, the temperature of the Earth increases as you get closer to the center, and this increase of temperature is known as the geothermal gradient. So it does change depending on where you are, like on the surface of the Earth, so it doesn't change the same everywhere. Like it might get hotter faster in some places than in other places. Also, if you start on the top of a mountain drilling down, or you start, on a beach drilling down, you're going to get to hotter areas quicker. And it also changes depending on which layer you are on the interior of the Earth. And then heat transfers within the Earth. Uh, our thing. You guys, I am my mental choo-choo. Choo-choo. Okay, so there's a process called conduction, and that is where heat just goes, it's like touching something, right? So like my coffee, I have a coffee cup right here and there's hot coffee in it, and if I touch it, it's like flowing through my hand, conduction. Can kind of think of it like that. So that's how heat flows in the crust. The material itself is not moving. It's just the heat is transferring through the material. Then there's also something called convection. And so this involves changing density of the material depending on the temperature. So when things get hotter, they tend to get less dense, and when they get colder, they're more dense. And so when things get hot and they get less dense, they rise. So like maybe hot air rises. And then when it gets cooled off and it gets more dense, it sinks due to gravity. And so this is a transfer of energy and a way that material flows. Heat flows in more fluid or plastic-like materials. And so all of that is coming from the core. And so these are those convection cycles that I was trying to talk about with the core. But a convection cycle is the same no matter what you're talking about, if it's air or water, but we're just having to talk about earth material here. And so there's also convection within the asthenosphere, and that convection cycles is what moves the lithosphere. And so we'll talk about this with um, the Earth's plates and continental drift. So here's the core, and let's think of this as the heat source for the interior of the Earth. Anything that's closer to the core, oh my gosh, you guys, what is happening in the world right now? Anything that's closer to the core with a C heats up, and that material gets hot and it rises because it's less dense. So if my mouse is a little earth particle and it's near the core, it gets really, really hot, it gets less dense, and so it floats, right? But as it floats, it's getting away from the heat source, it's giving off its heat, it's cooling down, it's becoming more dense. So it flows. Where is it sinking? And as it cools, it goes back down and sinks down, right? But as it gets closer to the core, it gets hot again and then it starts to rise. And there's these cycles that happen because of that, and they're convection cycles. Also, when we're talking about the interior of the Earth, we cannot leave out that the magnetic field around the Earth has to do with the independent rotation of the core from the mantle, and then also those convection cycles in the outer core. So knowing that the core and its rotation is responsible for Earth's magnetic field is important. Earth's magnetic field protects us from things like solar flares. It's what gives us magnetic north. A lot of animals use it to migrate. When we look at different cooling effects from things like the oceanic ridges and magma coming up, um, the direction of the atoms in there face magnetic north and south, and so it's an important part of Earth's functioning, and it is contributed to the core spinning independently from the mantle and also those little convection cycles in the outer core. Earth's magnetic field is changing. So here it's showing you in 1904, magnetic north was here, and it's shifted to 2005, which means it's now here. So in 2005, we were like here-ish, right? If you're looking at these two maps, 2011, it's gotten even closer to geographic north. And so magnetics field, it's always changed. We've known that our poles have swapped throughout history. So north was south and south was north. And we expect it to happen again at some point. We don't really understand what makes that switch happen. It's generally accepted that it doesn't happen overnight. And so if that did happen, we're not really sure what would go on. But the magnetic field around the Earth is also weakening. And so it's indicating that there's probably a shift that's going to happen like soon in a geologic time scale, probably not within our life. And it's really interesting because no one's ever experienced it before, and we're not really sure what to expect when the poles swap. Oh, yep, this is everything I just said, I believe. So when it says reversal takes only a few thousand years, only a few thousand, that's like what? But like in the time frame of the Earth, that's not a long time. And then we have new technologies. So this entire time we've been talking about seismic waves and earthquakes. Just know that there are new technologies that are beyond the scope of this class that are computerizing and trying to map the interior of the Earth. And yeah, so we have seismic waves, but we also have other ways to look inside the Earth. And here's a break. I'm going to break because I clearly can't talk. So this will be part one. There's probably going to be 4 parts in this lecture, probably, but we'll see how it goes. I hope you all, whenever you're listening to this, are having a fantastic day, and listen to the next part soon.